All right. Yeah. Thank you all for coming, and thanks to the organizers for the opportunity to give the talk and also to spend some time here at the Newton Institute. So this is kind of experimental talk, so I'm looking forward to feedback from participants and the audience in general. So here this is the I'm trying to bridge the gap between three different areas: machine learning, dynamical systems, and algorithmic information theory. And I would like to illustrate this through kernel methods. I mean, a lot of people here are fans of kernel methods. So I'm trying to reformulate kernel methods using insights from algorithmic information theory and kernel of complexity in particular. So this was inspired mostly through discussions with Marcus Hutter, who is currently at DeepMind. So Marcus believes that AIT is the key to AGI. Okay, I don't know much about AGI, but I'm mostly into dynamical system theory, so I'm trying to see if there is a way to adapt his arguments to dynamical systems. So this is joint work with all these people here. And so the main question here is how to analyze complex systems. So there are three approaches that I'm interested in here in this talk. First one is to characterize concepts like complexity, simplicity, and randomness. I mean, this is the object of algorithmic information theory that was developed mostly by Kolmogorov, Solomonov, and Chaitin about in the 60s, about 8 years ago. So it's it gives like very formal definitions of these concepts, but it's hard to compute quantities that appear in the theory, and in particular Kolmogorov complexity. The other field that is allowing to analyze complex systems nowadays is machine learning, which is quite popular. So it is concerned with the algorithm designed to accomplish a certain task whose performance improves with the input of more data. It allows the analysis of some very high-dimensional complex systems on the basis of data when the model is not even known. But among its limitations is that it's mostly a set of techniques and algorithms, and the theory is still underdeveloped, and it's not clear why the algorithms work and what is their domain of applicability. And then the most classical theory to analyze complex systems is the theory of dynamical systems that was mostly formalized by Poincaré and Lyapunov in the late 1800s. So it allows to analyze complex systems when the model is known. So it offers non-trivial ways to analyze the dynamical systems. It has the status of theory, but it is currently limited to low-dimensional models and some infinite-dimensional systems. So the idea here, the suggestion is try to see how to develop this framework where the three areas interact. The main objective is to give mathematical foundations to machine learning based on AIT and dynamical systems, mostly in the following directions. First direction is machine learning and dynamical systems, where the goal is to fill the gap between machine learning and dynamical systems in the following directions. So machine learning for dynamical systems, and the question is how to analyze dynamical systems on the basis of observed data rather than attempt to study them analytically. So here we are interested not only in prediction, but also in qualitative behavior of dynamical systems. So this would allow to extend the boundaries of the classical theory of dynamical systems and go beyond the database models, beyond the model-based analysis. And the other direction is dynamical systems for machine learning and how to analyze algorithms for machine learning using tools from the theory of dynamical systems. So here we would see algorithms as dynamical systems, where the time is the time in the computer, not on the clock. And this would allow to give a solid foundation to the existing method and understand their true potential and limits. Other direction is machine learning and AIT. So here we would have machine learning for algorithmic information theory. So here we'll be interested in applications of Solomonov induction, algorithmic probability approaches for probability predictions, and the links between information learning and data compression in view of developing or using machine learning algorithms for better compression and prediction, trying to approximate, that's the long-term goal, Kolmogorov complexity from data. The other direction is AIT for machine learning, where the goal here is to identify the domain of applicability of certain machine learning methods and explain, for example, why certain methods in machine learning will a priori work. So here the keyword is a priori. a priori work so well for certain problems, or a priori will not work for other problems. So here the idea is to look at compression and see how this will inform us on machine learning methods. So yeah, just to give, I'm just giving a lot of context here. So the direction machine learning and dynamical systems is mostly inspired by Steve Smale. I mean, this is what he mentioned about almost 20 years ago, where he said in the introduction of this book that the unification of dynamical systems theory and learning theory is a major problem. And another problem is to develop a comparative study of useful algorithms currently available and to give them unity. So he's one actually who motivated me and my other colleague to work on this area around the same time, like 2008. And so this is what we end up writing in one of the early papers we wrote. We said that it's easier to simulate dynamical systems and analyze the empirical data rather than attempt to study them analytically. But the mathematical theory at that time to analyze dynamical systems on the basis of their data is still largely underdeveloped. So that's machine learning and dynamical systems. And then, like most recently, as I mentioned, I started getting interested in the interface of AIT and dynamical systems, where here the goal is to look at data and look at probability complexity perspective on the data, especially for dynamical systems, and see how this would enrich statistical learning theories related to series prediction and analysis. So this would be, this is what we found actually, that it was interesting to look at the kernel complexity of data before starting to analyzing them and see if it will be easier to analyze them or not, especially in the context of problems where there is uncertainty and stochasticity. And the other direction is AIT and machine learning. And so here our goal is to reformulate algorithmic machine learning using tools from AIT with the aim of providing them a more solid theoretical foundation. So this is what we wrote in some of the papers recently. So here what I'm trying to say, I mean, just I forgot something here, is that, yeah, so this interface here, I'm trying to argue that kernel methods are the core, the heart of this diagram, that kernel methods will show up as a tool to unify the interaction between the three areas. Maybe next time I should write a circle here and put kernel methods in the heart of it, yeah. Yeah, so today I'll focus mostly on the interface of AIT and machine learning, and then I'll illustrate this interface through dynamical systems. So yeah, start talking about kernel methods. I'll go quickly over them because I think like most of the people here are experts in kernel methods. And then I'll talk about sparse kernel flows, which is like a method that we developed to learn kernels from data that we apply to learn chaotic dynamical systems. And then I'll talk about AIT for kernel methods and kernel methods for AIT. So we'll talk about kernel complexity-based kernels, how we define them, and then we see how to compute them. And then we'll see how we can use the AIT for kernel methods and use the principle of the minimum description length and have a reformulation of sparse kernel flows and show that sparse kernel flows is a natural way to learn kernels from data, and that it follows directly from AIT. And then this is like supervised learning. So basically we'll have kernel methods for AIT, AIT for kernel methods, and then we have supervised learning and then application to also unsupervised learning. The other application is AIT for kernel methods and application to unsupervised learning. And then we'll talk about this principle that was developed by Marcus Hüter, and then we'll see how we can use it and extend it to learning kernels in kernel density estimation and for clustering. And then the other direction is kernel methods for AIT, where we show that HSIG, for example, it can be viewed as an approximation to algorithmic mutual information and other like an normalized compressed distance that both show up in AIT. And then the third part is to look at problem of simplification of PDEs using non-order transformations and also to Poincaré normal forms, where we could learn them using kernel methods and see how it's possible to reformulate them using an AIT perspective. So there is a lot of material, but again, feel free to interrupt whenever you feel so. So I'll go quickly over this. So RKHS, I mean, they appeared in the 30s as an answer to the question, when is it possible to embed a metric space into Hilbert space? And if another question was, the answer at that time was that if the metric satisfies certain conditions, it's possible to embed a metric space into a special kind of Hilbert spaces that are called RKHS. So then there have been a lot of activity in the 50s and the 60s, mainly through Aronjan and Schwartz. And then they died a little bit, and then they were resurrected through Wahba and in the 90s, and then Steve Smale in the 20s, and then there have been a lot of activities since then. So then these are the definition of RKHS. So basically there are Hilbert spaces with reproducing property, and where the reproducing kernel has a span that is dense in H. So as I said, I'll go quickly over this. So I mean, they are very useful in learning theory, for example, where the goal is to learn unknown functions from random samples. So the error function, or the empirical one, is the following one. So I said I'll go quickly over kernel methods, because I think most of you know kernel methods here. So yeah, so then you find the represented theorem. So that we have the linearity in the feature maps, and the coefficients themselves will satisfy a system of linear equations. And the natural question here is how to find the kernel. And so here we just come back to the same problem, which is like learning an unknown function from random samples. So here, I mean, this problem is, in general, is an ill-posed problem, but in the setting of optimal recovery, this problem can be turned into a well-posed problem by restricting candidates for you to belong a certain Banach space with the following norm, and turning this problem of learning these functions to the following min-max problem. So where U is the approximate from the full data set, and the V is from a smaller data set. So basically, this is based, the method of kernel flaws is based on the following premise, that a kernel is good if there is no significant loss in accuracy in the prediction error if the number of data points is halved. So that's the key somehow. I mean, that led me to start thinking about compression and AIT and Kolmogorov complexity. Because again, so what we are saying is that if we reduce the number of data that we are using, then there is no significant loss in accuracy. So which means that there is, it's possible to compress the data to a certain number without losing accuracy. So in practice, this is how kernel fuzzy is used. One just introduces the following relative error, rho, which is V star minus Vs, with norm square in the numerator and the denominator. And so V star is the interpolant with the capital N points, and then Vs is the subsample with capital N over 2 points. But again, don't focus too much on the N over 2, because we want, so we are interested in compression. So we want to just, so this number will be just like a smaller number, and we want to push the compression argument in the, as much as possible, especially in the, by making links with the Kolmogorov complexity. So this is how it works. So if we have a family of kernels k theta x prime parameterized by theta, the kernel flows algorithm can then be described as follows. So we have a large data set. First, we take a sample of size n, like randomly, and then from it, we take another subsample of size capital N over 2, and then we construct the following relative error, and which will be parameterized by theta, and then one would evolve theta in the gradient descent direction of rho, which is theta k plus 1 is equal to theta k minus delta gradient rho with respect to theta. This is, in a way, this is like a trainable machine learning method that is not necessarily a neural network, but so where the goal is to learn the parameters of the kernel through gradient descent. So we applied this to a problem of learning chaotic dynamical systems. So we have a time series x1 to xn, and our goal is to forecast xn plus 1 based on x1 to xn. So we just work on the assumption that this time series can be approximated by the solution of a dynamical system of this form, where we have a time delay. And so here in the simulation, we assume that tau is fixed, but then there is a way to learn it actually also using kernel methods. And then we are going to just recast this as a problem of learning an unknown function from random samples, where the y is zk plus 1 and the x is the past. So yeah, so based on what we saw, I mean, this is a closed form expression of the approximant. But then since we are, as you said, I mean, when we are learning a dynamical system, I mean, it's not necessarily only about prediction. So we are also interested in the qualitative behavior. So we just develop different variants of kernel flows that are related to dynamics. So the first one is the relative error that is related to the short term. Second metric, so here we said that a kernel is good if the approximation of the maximal Lyapunov exponent with capital N points versus capital N over 2 points doesn't change much. But we can also introduce other Lyapunov exponents if you are interested in other qualitative behavior, not necessarily only the very long-term one, but also maybe short-term. So this is, as I said, so this is short-term, this is long-term. Then we also introduce another way to learn the kernel based on the MMD, where we say that I forgot to introduce the maximum mean discrepancy, but it's like a kernel-based metric between probability measures. So here we'll say that the kernel is good if the MMD between two subsamples of the time series doesn't change much. So in all cases, I mean, they are all parameterized by theta, and then we run gradient descent. So here, the goal here is to capture the statistical properties of the dynamical systems. And the last one, which is related to the attractors. So here we assume that we have a reconstruction of the attractor with capital N points versus capital N over 2 points. And we'll say that kernel is good if the Hausdorff distance between the construction of the attractor with capital N points versus capital N over 2 point is not doesn't change much. And you see, we got like a short-term, long-term, statistical, and geometric behavior of the dynamics through trying to learn the kernel accordingly. So what we did here is that we also, the question is how to, which kind of kernel do we choose? So the idea here is to just choose a large dictionary of kernels, and then, so which are the elements ki parameterized by beta. So the theta I here are the coefficients, and the betas are just like other parameters, like the sigma in the case of the Gaussian kernel. And then we sparsify, so we add an L1 penalty to the criterion. So here, I mean, this is like this can be changed, so if this is short term, we could keep the illustrative error. If it's long term, we can put Lyapunov exponents here, or MMD if we are interested in statistical behavior, or Hausdorff distance between the attractors, construction of the attractors if we are interested in geometric behavior. And then our goal is to trying to learn an entire database of chaotic systems. So here's 131. We started initially with 131, but then the database got expanded to 135. So one of my students, he also tried to the updated one, and the method still worked. So we use this kernel, which I think has 40 parameters. And then our goal is to see if this kernel can allow to attack this entire database of 131 dynamical systems, and it worked. So we just you see we have the classical Gaussian polynomial kernel, but we have also kernels that capture periodic behavior, locally periodic behavior. We have also the triangular kernel in both cases. So we tried it. I mean, these are, for example, one 3D example from chemistry. The database has many elements from different applications. I mean, in chemistry, we have this following 3D ODE. So this is like the reconstruction of the attractor, true versus approximation. Like this is like before learning and after learning the kernel. This is like another example from electronics. And so before and after learning the kernel, these are the different attractors. And we see here, for example, that these are the coefficients that we had. Some of the coefficients in the kernels in the large kernel get zeroed, And we have two criteria. So the SMAP is for the short-term prediction, and we see if we move from regular Kernel flows without sparsification, and then with sparsification, the error gets reduced for this example. Same thing for this example. Hausdorff distance is for long-term behavior. Also, we have a reduction in the errors. And yeah, so now we want to see. Yeah, so we got like consistent results. I mean, we had like statistical analysis of for the whole system, and then we have consistently that we are having better results when we are dealing with sparse kernel flows to learn chaotic systems. So you can look at the papers that are corresponding. So now we want to see how this method, for example, and also the problem of learning kernels from data can be reformulated using AIT. And as I said, we are going to look at two directions, AIT for kernel methods and kernel methods for AIT. So, so AIT here will inspire kernel design. So we'll have kernel complexity-based kernels. We'll have also MDL clustering and loss rank principle for KDE and clustering. And then kernel methods for AIT. This will provide practical approximations of AIT measures. If you remember, we said that one of the problems of AIT is that it's hard to compute the main quantities there, and then we want to use kernel methods for that. And we'll show that the normalized compressed distance and algorithmic mutual information can be approximated using kernel methods. And here we make the link between algorithmic mutual information and HSIG. Yeah, so what is AIT? So it's directly related to computation, computability theory, and information theory. Yeah, so I think one of the famous books in information theory is by McKay, where he says that machine learning and information theory are two sides of the same coin. And here we want to push the argument a little bit further and say that machine learning and AIT are two sides of the same coin. So that's somehow the long direction that we want to pursue. So the main quantity of AIT is Kolmogorov complexity, which measures the complexity of an individual object as the amount of information required to describe or generate X. So basically, simply said, it's just the length of the shortest program, P, that allows to generate X once we input it into a universal Turing machine. So that's the technical definition. But intuitively, I mean, this is what all we have. For example, if we take this example, take this sequence, 1, 0, repeated 8 times. So it's easy to encode it in a code and then in a program and say just like print 1, 0, 8 times. So this would be the length of that program, whether it's in Python or any other language that you like. I mean, it will be easier to just write it simply like that, print 1, 0, 8 times. But if the sequence is random, then it will be hard actually to generate anything. Maybe it will be hard to generate a program that does the same. So if we have a sequence of 16 elements that are totally random, then the Kolmogorov complexity will be approximately equal to n bits. So that's essentially what Kolmogorov complexity is. And yeah, so the link here, I mean, this is the intuition that the link between kernel complexity and kernel methods seems natural. I mean, we just start with what are kernel methods. So kernels are a measure of similarity, and kernel complexity is about compression. So it's natural to say that two objects are similar if they can be compressed to each other. So that's the general direction. So this is what we have in this conditional kernel complexity. I mean, it's saying that it's the length of the shortest program that computes X from Y. So in a way, so we could see, if we look at this definition of the conditional kernel complexity, we could see a similarity that is already showing up, right? I mean, kernel, reproducing kernel is a measure of similarity. Conditional kernel complexity is saying that if we have X, what can we say? If we have Y, what can we say about X? So it is the length of the shortest program to output X given Y as extra input. So if Y is uninformative or unrelated to X, then Kx given Y will be essentially the same as K of X. But if Y contains a lot of information relevant to X, then Kx given Y will be significantly smaller. I mean, that's as I said, is the main intuition here. And so this leads to defining Kolmogorov Kolmogorov complexity based kernels. So here, one of them is the following: is the kxy is equal to exponential minus lambda dk xy. So here, which is basically we take the symmetrized Kolmogorov complexity, conditional Kolmogorov complexity. So we take k sim as the max of kx given y versus ky given x. We just take a delta, just a sort of regularizer to make of this metric for some cases, and then we define the reproducing kernel as the exponential of minus lambda dk xy. So this kernel will provide a measure of similarity between x and y, where smaller values of k sim correspond to a greater similarity and larger values indicate dissimilarity. So that's one reproducing kernel based on conditional Kolmogorov complexity. Another one is based on algorithmic mutual information, which is this object here. So kx minus kx given y. So essentially, it's just saying that if we have kx given y contains a lot of, so if there is a lot of information of y contained in x, then this object here will be smaller. So kx given y will be close to kx, and otherwise will not. So this difference will be larger. So this is the other kernel that we got which is the symmetrized algorithmic AMI kernel. So this expression quantifies how much knowing y reduces the complexity of describing x. And if y contains significant information about x, then kxy will be smaller than kx. And so essentially, the kxy will reduce to k capital X. Otherwise, this will be smaller. Yeah. So here, the kernel captures the strongest informational relationship between x and y, and so the similarity measure will be is enforced from this point of view. And the third Kolmogorov complexity based kernel is based on the normalized compression distance. So here we take the joint sequence xy. So this we compute the Kolmogorov complexity of joint xy, and then we take the mean of cxcy. So this will be this is the definition of the NCD, and then we just take a reproducing kernel, which is given by the exponential of minus lambda NCD xy. So this is like the third kernel that is inspired by AIT objects. Yeah, so another question here is how universal are these kernels? So this is like still like an open problem. Then another question is how do we compute actually these objects? So this is like we are still working on that, but like we came up, there are a lot of compressors like Lemperzik and different variants. So we just use these to compute the relative Kolmogorov complexity. So here, to use this kind of software, that is already existing, we just approximated ky given x by kxy, which is like the expanded sequence minus kx. But yeah, finding compressors that are related to relative Kolmogorov complexity is still like an open problem. So this is also worth exploring. So that's that. Yeah. Okay. Now we are going to move to another principle, which will allow us to reformulate some kernel methods using AIT perspective. So we'll start with this minimum description length. So this is like a principle that provides a criterion for the selection of models, regardless of their complexity, without the restrictive assumption that the data form a sample from a true distribution. It can be viewed as a downscaled practical version of Kolmogorov complexity. So here, the advantage of this principle is that it recommends the compression of both the data and the model. So it's not only about reducing the number of parameters in the model or reducing the number of data, but it's both. So we want to compress both the data and the model. And so the better the compression, the more regularity has been detected, and the prediction will be better. So this is, in a way, formalization of Occam's razor, where that allows, that recommends the selection of the simplest model consistent with the data. But again, we want to use both. We want to compress both model and data. And it says that the best model is the one which permits the shortest encoding of the data and the model itself. So this is it's the addition of the code length, which is based on the Kernel complexity of the model, that makes it different from the familiar maximum likelihood principle. And yeah, so that's that. So basically, this is what happens, that you take a set that contains everything that you know about your models, about your system, whether it's like models or theories, hypotheses, probabilities. I mean, you can just put everything in M, and then you sorts them out using the corresponding Kernel complexity. So we have K of Qi, which is the Kernel complexity corresponding to whatever you know about your system, as I said, whether it's a model or a theory or probability descriptions, etc. And then, so the MDL will be to take the model that reduces, that minimizes minus log Q plus KQ. So minus log Q is coming just from the way we are going to encode the data, and KQ is about the model. So this is like you see for each Q, we are going to have a minimal description, which is a minus log Q, and then we add the complexity to it. So basically, MDL is recommending to choose a model, which is the argument of Q in M of minus log Q plus K of Q. And then you see, if you compare it to regularization in machine learning, there we are recommended to take to minimize the loss plus the regularizer. So you see the difference is that, yeah, instead of having linearity with respect to lambda, so the regularizer here is fixed. So K of Q is a term coming from AIT. Lambda times R of F is coming from classical approaches in machine learning. The loss here has to be like log loss. In machine learning, the loss can be anything. So in a way, there is a link between both approaches. And so yeah, so it's this that allows us to reformulate sparse kernel flows. So as we said, I mean, here the difference and commonalities, as I said, is that the MDL principle is completely general. It makes no assumption whatsoever on the underlying model class. So there is no IID assumption, no stationarity, no ergodicity or parametric or smoothness assumptions, while regularization in machine learning is somewhat tailored towards IID data. MDL is limited to log loss, while any loss can be used in regularization in machine learning. Regularization in machine learning requires choosing a penalty R and then tuning its strength lambda, but MDL dictates the penalty term coming directly from kernel complexity. Yeah, so then the term, I mean, there's a term that always shows up in the kernel complexity, which is like P over 2 log n, where P is the number of parameters and capital N is the number of data points. And this like just comes naturally from Bayesian perspective. So here, each parameter can be only estimated to a precision proportional to 1 over square root of n. And then by just taking the minus log, we'll get n log n over 2. And yeah, if we have like p parameters, then this will become the kernel complexity will be p over 2 log n. So it's basically it balances model fitting and simplicity and prevents overfitting. So yeah, we proved in the paper, I mean, that yeah, that there is a way to reformulate the problem of learning kernels from data as the following one. Again, I mean, this is not really an important thing. I mean, it can be anything. The main thing here is just the p over 2 log n, where I explained where I just explained where it came from. So if we have a kernel that is contains a lot of elements, so sum of theta I square ki xy parameterized by beta. So the method of sparse kernel flows is recommended to just take a look at the argument of beta, theta, and p of the following criterion. So and we show that it's coming from through compression arguments, and but this, I mean, would require solving 2 to the power m optimization problems. But here in practice, what happens is that we also show that actually we can approximate this by the sparse kernel flow. So basically, sparse kernel flows is coming directly from an AIT perspective. So this term, log down norm of theta 1, is just surrogate loss corresponding that comes from this AIT loss. But with the advantage that it is convex. So basically replacing the MDL regularizer by the L1 regularizer is a form of a surrogate loss, but for regularization. And here the idea was just to simplify the computation, but still the AIT flavor is still in the way we learn the kernel. And so yeah, so what we proved basically is that the sparse kernel approach is the natural way to learn kernels from data. There is no need to use cross-validation to justify its efficiency, and everything follows from AIT. So we didn't follow basically the statistical route to justify that sparse kernel approach is the natural way. We just used a different way, which is the AIT way, where we didn't even use cross-validation to prove the results. And as I said, I mean, the fact that we have compression is just coming naturally from compression arguments that follow directly from AIT. And yeah, so as we said, this method considers that the kernel is good if the number of points can be halved, or it can be compressed, basically, if you want to use the language of AIT, with no loss in performance, plus we reduce the number of parameters in the coefficients in the kernel. So basically, this is consistent with MDL, where we are compressing both data and coefficients. And here, I mean, we still don't know. I mean, we didn't prove which points we should use, but conjecture that it's these are the covering numbers that show up in learning theory. Now, I mean, like, we want to. So here we were talking about learning unknown functions from random samples and application to learning dynamical systems. Now we are going to look at another problem, which is the problem of density estimation, which is like an unsupervised learning. So the minimum description length suffers from certain technical problems because it's still like a parametric way of doing things. And yeah, so it doesn't work well. And we can look at the paper where we showed actually the MDL doesn't work well when it comes to learning kernels in kernel density estimation, because it still depends on the data. And so there was a need to look at another principle in AIT where we could learn, for example, kernels in KDE. So KDE is saying that the estimate of probability measure is just given by 1/n k theta x xj, and the actual question is how to learn theta in a given kernel. And this is where this principle, the loss rank principle, comes in. So it generalizes the minimum description length to more flexible models and arbitrary loss functions. And so for each data set and model parameter theta, LARP defines a rank. So there is this concept of rank for given x by counting how many hypothetical data sets x prime achieve a loss such that the loss of theta given x prime is less or equal than the loss of theta given x. So in a way, so this gives us an intuition about what kind of parameters are robust to unseen data. And so this is what leads to what is called the code length. And so here we propose the following approach. So to learn kernels in KDE using LARP, so we proceed as follows. So we choose a kernel, could be also again a sum of smaller elemental kernels that are parameterized by theta. So we consider our data, so which is the x1 to xn. So the kernel density estimate is given by the following class form. And then we define the loss function by computing the negative likelihood of the observed data under the KDE model. So this loss measures how well the kernel with parameters theta describes the data set X. And then to be consistent with LARP, we are going to use another hypothetical data set, which is X prime, which is like another data set that we generate. I mean, here in simulation, we just use like a uniform, but it can be anything. But the question is to find what is the best hypothetical data set is also another question. So as I said, we choose X prime to be sampled uniformly within a bounding region determined by X. So these are data sets that serve as alternatives for evaluating how typical the observed data set is under the kernel defined by theta. So basically, we just compute this rank, which is the cardinal of the elements in the hypothetical data sets that achieve that the loss of theta given X prime is less or equal than the loss of theta given X. And so the smaller the rank, then you are going to will be able to see how many data will achieve a smaller less, and higher rank indicates that X is more typical under theta. So smaller code, I mean, that just indicates that kernels that both describe X and generalize to hypothetical data sets X prime. So we are trying to get the best of both worlds. So we want to fit our data to the kernel and to also generalize to alternative data sets. But again, as I said, by using the experiments, just turned out that this is like sensitive to the original hypothetical data set that you choose. So the question there is what would be the best hypothetical data set that we choose. And then the kernels, I mean, we just have to find the argmin of this log rank of theta given X. So that's the general idea. So we tried it on a smaller, on some simple toy model. So there is like more work that needs to be done here. So we just take a weighted mixture of Gaussian and non-Gaussian kernel, and we computed the KDE, and then we just did the following. So we need to learn the parameters like sigma, h, alpha Gauss, and alpha epan. So we computed the negative likelihood, and then we computed the approximate rank approximation, which is, as I said, in this experiment just took a hypothetical data set which is uniform, and then our goal is to minimize the rank, which is the cardinal of the number of hypothetical data set with negative log likelihood versus observed negative log likelihood. And so this is the point that we needed, the quantity that we wanted to minimize, which is the log of rank plus a smaller object, just to have like a numerical stability. And we just did a grid search that for the parameters that allow to minimize that object. So I'm sure, I mean, I tried gradient descent, but just took a lot of time to convert. So grid search was much better in this context, probably because of the low number of parameters. So here we just looked at histograms, but there's probably a better way to measure, for example, by looking at other metrics between probability measures. So here, for example, this is the data histogram that we generated. This is the KDE before learning the kernel, and then KDE after learning the kernel using LARP. So that's this direction. Any questions so far, or a lot of questions? Yeah, anyway, we can discuss later. Yeah. Then you have now we are going to move to the other direction, which is kernel methods for AIT. And we proved that HSIC constitutes an approximation to algorithmic material information. So here, what is algorithmic information? Material information is just the following object. So it's basically related to the shared algorithmic information between two objects, X and Y. So essentially, it's just the kernel complexity of X plus kernel complexity of Y minus the joint kernel complexity of the joint X and Y. So high AMI indicates that X and Y share a significant algorithmic structure versus smaller one will lead say that there is no significant algorithmic structure, and this is where somehow it sounds natural to relate this to H-seq. So the Hilbert-Schmidt independence criterion is popular in kernel methods to measure independence between two variables in RKHS. So it measures the dependence between by evaluating the norm of the cross covariance operator over an RKHS. So it's computed as follows. So you see H-seq capture dependencies between X and Y by embedding data into an RKHS and then computing the cross covariance operator. And yeah, so what we proved is that H-seq is an approximation of the algorithmic material information. But you see, conceptually, they also seem similar, right? I mean, H-seq is a kernel-based measure of statistical dependence. AMI is a measure of algorithmic dependence. And so it sounded like natural to capture the link between the two. So their aim is to capture dependencies between variables and objects, but from different perspectives. H-seq is statistical, kernel-based, while algorithmic material information is complexity theoretic, and so it's an AIT perspective. So then it's natural to see if there is a way to find kernels that link the two, and that's exactly the kernels that I talked about at the beginning. So by choosing suitable kernels, H-seq can approximate AMI, so making it a practical proxy for algorithmic notion of dependence. And so here again we are bridging the gap between statistics and AIT via kernel methods. And so that's the kernel I was talking about. So if we choose this kernel, compression-based kernel, which is exponential minus lambda normalized compressed distance between X and Y, we can show that H-seq approximates AMI. And yeah, so here, I mean that, yeah, so it just has some implications. So there's a shared information that is between objects that are captured by two objects. So which is one is statistical and the other one is algorithmic information, algorithmic information theoretic. So we get both words talking to each other via this kind of kernels, and then being able to capture this kind of connections. So I said here, this approach unifies statistical dependency measures and algorithmic information measures. And yeah, so, but then a lot of work remains to be done about which kind of kernels and which kind of compressors we need to use in practice. Universal kernels like that we are familiar with in kernel methods, they are suitable for algorithmic material information and normalized compressed distance, and they can capture arbitrary dependencies. Characteristic kernels, they preserve all distributional information in RKHS, and then in numerical experiments we saw that small sigma is better for AMI, larger sigma may miss algorithmic dependency. So again, the question there is always the choice of the kernel. Yeah.
I may have missed that on your presentation, but we have defined kernels for the IIT, such as NCD, etc. But concretely, how does this like those definitions apply to IIT, like concrete applications for kernel methods in this context?
So how can we use kernel methods in AIT?
No, actually, by using, or where could we use kernel methods in AIT?
Yeah, so so I said at the beginning, one of the problems of current limitations of AIT is that you cannot compute a lot of objects there. So AIT is a nice theory, so it characterizes a lot of things, but most of the objects there, you cannot compute them from data, like conmod complexity, normalized compressed distance, algorithmic material information. All of them, I mean, they are like very nice theoretical objects, but then how to compute them from data is not clear. So here the argument is I'm trying to say that kernel methods are the way or a way to compute these objects that are important in AIT, but that usually we cannot compute from data. And so this is what I did here, that by showing that H-seq can be computed from AMI, and then we can construct kernels that actually that are common complexity based kernels that allow to compute objects in AIT.
So it gives us a statistical measure for complexity as well.
Yeah, exactly. Yeah, yeah. Somehow that's the idea that we that by bridging AIT and machine learning via kernel methods, we are able to have computable computational way to compute some objects in AIT. Yeah. Yeah, is it clear?
Yes.
So that approximation you put up, that H6 was approximately the mutual information. That's not true for all kernels. That was only for this particular kernel. That
yeah, for this particular. So yeah, you can note. Yeah. So this is why I'm saying here that you see, it's sensitive. So we can use the universal kernels or characteristic kernels in general, but then they are sensitive. There is a sensitivity there. So for the kernels that we talked about, yeah, the common complexity based kernels, yeah, we can prove that it works. But then it doesn't mean that it's the only one that works. Here, what I showed in the simulation here is that some of the non-kernels, like Gaussian or Laplace, etc., they may work or may not work. So yeah, we can probably do it the other way around, where we take our kernels that we know and see which ones are best for AIT. But still, it's still an open problem. Yeah.
Just checking you got an eye on the time. We've got about 10 minutes left.
Yeah. Okay. Yeah. So yeah, I'm finishing. Yeah. Yeah. Okay. So yeah. So actually, this is answering your question. Kernel methods provide practical approximation of intractable AIT quantities. H6 approximates AMI, enabling dependency detection via compression-inspired tools, and choosing appropriate kernels is critical for success. Yeah. Then since we don't have much time left, I'm just going to go quickly over the last part, which is like simplifying PDEs using kernel methods and Poincaré normal forms. And then I want to just show that this can be understood from an AIT perspective as well. Yeah. So just basically coming back to dynamics, where I started my talk. Yeah. Okay. Yeah. So for PDEs, I mean, we have linear PDEs that many of them are understood. Nonlinear PDEs are harder. And then another question is, which kind of PDEs are we able to, nonlinear PDEs are we able to map into linear PDEs? And yeah, an example is just a famous example is the Kohlhoff transform that allows to transform the Burger's equation to a linear equation. So yeah, that's an example, like from burgers to heat. So this is the Kohlhoff transformation. And yeah, so what we did is that we just thought, I mean, okay, the idea was to map nonlinear PDEs to linear PDEs, but then we assume that we don't know what the PDEs are. So is it possible to use kernel methods to do that? And yeah, so this is what we did here. So just a database discovery of the Kohlhoff transformation. So basically, this is how we constructed the framework. So we just have to minimize some RKHS norm to discover the transformation. We generalize we use like a generalized representative theorem. Yeah, so this would be the transformation, but we have using a generalized representative theorem to find the data, the transformation from data. And yeah, this is what we got. So we got good results. So we recovered the heat equation from the true versus approximation, and also even the Kohlhoff transformation true versus approximation using kernel methods. So here we are not using kernel methods to reconstruct the solution. We are using kernel methods to find transformation that maps a nonlinear PDE to a linear PDE. Yeah, so here, yeah, if we come back to what I started about the MDL principle, so here the problem of simplifying PDEs using kernel methods is consistent with the MDL principle, since we are using the simplest model as a target, and we are also using minimal number of points and parameters via sparse kernel flow. So here we also use sparse kernel flows to learn the kernel. So and then we proved actually that this is consistent with the MDL principle. And the last part is about Poincaré normal forms. So we have a nonlinear ODE, and the goal is to simplify it using transformations. So yes, Poincaré's program was that, yeah, if we have a nonlinear ODE, we just perform Taylor series expansion, then the goal is to get rid of the maximum number of terms in the Taylor series expansion. And yeah, so our goal was to just, in a way, canalize Poincaré normal forms. And so we had to go through this homological operator that Poincaré introduced, where he proved that the terms that cannot be removed are in the kernel of this homological operator. And then we use basically kernel method to solve this PDE. Which is like canalizing Poincaré normal forms, which is looking at this kind of objects here. So looking at either the kernel of homological operator or its orthogonal complement, and and that's this is what we also proved there, that this is also consistent with the MDL principle, because by using data, we are also trying to minimize the number of terms. So you see, it's also, there is a sense of sparsification, but like a more complicated way, but because we are looking at the homological operator. And then we are also reducing the number of points using sparse kernel flows. So we applied it to a simple example here, which is like a brucillator that has a hop bifurcation. And you see, we have the true normal form that also, so again, when we are dealing with dynamics here, the key is not only to learn the solution, but also to learn the qualitative behavior. And here you see we are learning the limit cycle. So this is the true limit cycle, and then this is the learned limit cycle using kernel methods. And so that's the radius of the limit cycle, true versus learned versus approximation. And this is the evolution of the dynamics over time. This is the 3D representation of the limit cycle. And okay, so what we did here is that we introduced the method of sparse kernel flows and showed that it is efficient in learning a large database of chaotic dynamics. So we have formulated this problem of learning kernels from data using the MDL principle. And we showed that the loss involved in learning kernels using sparse kernel flows can be viewed as a problem of data compression, and that the problem of learning kernels from data can be viewed as a problem of choosing the shortest description where the MDL principle can be applied. So here we showed essentially that sparse kernel flows is consistent with Occam's razor. We also introduced kernel complexity-based kernels, and we showed that AIT perspectives can be used to learn kernels in kernel density estimation by choosing the shortest description where the loss rank principle can be applied. So this also showed, as we said, that it is not necessary to use cross-validation arguments to justify the efficiency of learning kernels from data. So it's not necessary to use the statistical route to argue for machine learning methods, and we can work directly with kernel complexity. So we also looked at the problem, quickly at the problem of simplifying ODEs and PDEs, either by working directly on the right-hand side of the equation or by mapping them to simpler models. But you see here, simplicity, we show that it's consistent with the AIT. And our ultimate goal is to reformulate other methods in machine learning and dynamical systems from an AIT perspective in view of giving them more solid foundations. All right. Thank you for your attention.
Thank you. Questions?
Yeah. Yeah.
So I was surprised by what you say about so your criterion to learn the kernel.
My what?
Your criterion to
Yeah.
The kernel is based on a square law solution problem that you look at on one data set.
And half of it or subsample, yeah.
And so, first, you did not use the regularized calibration regression where any condition where the matrix that you mentioned.
No, we use actually, yeah. So it's used actually, yeah.
Okay, but my point was, so have you looked at a given kernel this time, a different value of n. I mean, this is arbitrary, right? Half.
Yeah, exactly. Yeah, exactly. This is what led to complexity, because the half for me it didn't really make sense.
Yeah, exactly.
So this is why I thought it's really about compression. Yeah.
Yeah. Okay. So yeah, because at some point you say, okay, once we have this estimation, we don't need any more one out or.
No, this is important. Yeah. Yeah.
Yeah. So I mean, interestingly, you are comparing interestingly two estimation on two different data sets. So I mean, it is also well, you can measure. I mean, how much it's depending on your data. I mean, so
Yeah. There is always like leave one out, or yeah. It's always there.
Yeah.
So here we just showed. We just showed that this follows. Is not the fundamental thing we are looking at. That this follows from that. That's all. I mean, that's in a way we are just showing that it is a natural thing to do.
Yeah,
that's all. I mean, it's more of theoretical contribution, but we are not revisiting the method. The method is still based on using half. So cross validation, in a way, we are saying that it's like it follows from AIT. But in practice, when you start coding, this is exactly what happens. You have to do cross validation. Yeah.
Okay.
Yeah.
And second, so after you switch to defining different kernels and it's to the operation at some point, different kernels with link with algorithmic information theory. And so some of them are not semi-definite. They're not positive definite kernel.
Yeah, so yeah, exactly. But this is why actually, that's a good question. Yeah. So this is why we had to introduce, I went quickly. This is why we had to introduce these deltas, right? Yeah. So we have to find actually the right coefficients to make of them positive definite kernels. Yeah. But they are not positive definite kernels for all lambdas and all deltas. Yeah. So we just have to pick up the subset for them. Yeah. But you are right. That's the yes. All these kernels here, they are not necessarily always. They are not positive semi-definite for all lambdas, but some of them they may be positive semi-definite. Yeah.
How do you know when they are? I mean, that's kind of crucial.
But
the kernel method, you must have
but as I said, we just choose actually the parameters that allows it to be positive semi-definite.
But how do you know what they are?
You just when you are implementing it in practice, right? You just choose the lambda and the delta that allows you for it to be positive semi-definite. Yeah.
For all x and y.
Yeah, I mean that's the goal.
You have to test them for every.
For the ones that you have for your data. Yeah. So as I said, it's heavy. I mean, it's still not. These are like theoretical results. I mean, we still don't have actually a proof that there exists delta and lambda for all x and y. But for a subsample, for finite dimensional spaces, we have a proof that if you project it on, if you have a finite number of samples, then you can find lambda and delta. But if it's like for all of them, then we don't have a proof for that actually.
Yeah, that's usually this Schoenberg theory. That's the key problem.
Exactly. Yeah. So exactly. So we use actually one of Schoenberg results that to get actually a negative result, that they are not for all. If you are working in infinite dimensional space, then you can prove that they are not positive semi-definite. Yeah. So that's we specifically use like Schoenberg's result. Yeah. But then for a finite number of data points, then it's possible to find lambda and delta. Yeah. And this is also valid for all the other ones, actually, for the other kernels.
I was really interested in the last part you talk about.
Yeah, this one as well. Yeah, the eta. I mean, you see there are always terms here, the lambda and the eta, and sorry.
Sorry, I didn't mean to cut you off. I was going to tell you, I've got a question about the last part of your talk about linearizing nonlinear PD. It wasn't clear to me what you were learning from. Is that from realizations, from solutions to the nonlinear PD?
Yeah, exactly.
Or from the equations?
No, from the realization, we assume that we are having data directly, yeah.
Oh, so okay, so you assume your data here is observed solutions for different parameter values.
Yeah,
Yeah.
from the nonlinear PDE, and then we are trying to map it to a linear PDE.
Yeah.
So we assume that we don't know the origin, so which is like a nonlinear PDE, and then we are trying to find a mapping that maps it to a known PDE. In this case, it was the heat equation. But essentially, the goal was to find like the main linear PDEs, like wave, heat, Laplace, etc., and see if you can map your data to one of them by learning a nonlinear transformation, which is like the kernel. Yeah.
Nice. Okay, if there are no more questions, let's have the speaker again.
All right. Thank you.